So to me, my title screams two questions, and the first is which system would we like to simulate? And so specifically, we want to look at specifically two level emitters and an ensemble of them all coupled through a radiated path. From there, we want to see what their intensity profiles want to look like. So when I say intensity, you should think just the number of photons emitted per unit time. When we have them all very far separated from each other, they do exactly what we would expect them to do and follow this exponential decay. But as we bring them very close and near to each other, something very non-trivial happens where we get this burst of radiation. And then there is also this smooth transition between them. Now, this phenomenon is well known. This has been known for some time, since the 1950s. It's called superradiance. And it is this burst of intensity that is induced by a buildup of coherence, which we have highlighted here on the right-hand side of this equation in red. Essentially, it's just how much your emitters in your ensemble are speaking to each other, or how indistinguishable they are. Now, superradiance is, in order to have superradiance, your system must meet a number of requirements. Number one, that you've already spoken about, is spatial confinement. So all of your emitters need to be well within one emission wavelength of each other. Number two is you need spectral homogeneity. And by that, I mean that the independent emission spectra from each emitter should overlap with the next significantly in order to enable this. And third, we need spin alignment. So all the spins need to be aligned with each other. We were, in this project, not so interested in the last one, although we can use our algorithms to study this. We are more so interested in the first two, and specifically spectral homogeneity, which we'll talk more about later. So the next question is, why use quantum algorithms to do this at all? And the answer is because this is a fundamentally quantum question. This is a fundamentally quantum problem. And so what quantum computation will allow us to do is scale. So as quantum computers get better and better, our algorithms will be able to handle system sizes that are bigger and bigger that classical computation just will not be able to do. And the way that this works is we start with our Hamiltonian. This is true for any quantum simulation, but in our case, it's the many-atom Weisskopf-Poggian Hamiltonian. Then we cubitize that Hamiltonian, meaning we map all of the operators within the Hamiltonian to quantum gates. We then initialize our state and build our circuit. We then time evolve it using trauberization, and then we measure our state after some time t. Do that many times to get the number of statistics that you need, and then we calculate our observables. So specifying our model even further, we have this Hamiltonian. This is that many-atom extension of the Weisskopf-Poggian Hamiltonian that I mentioned. And we're going to model each atom with a single qubit. This is a relatively natural mapping because the atoms that we assume are a two-level system, they're two-level emitters anyway. Now, we then model the modes with some n number of qubits each. N can be 1 or it can be greater than 1. The reason why we need that is because in a bosonic mode of radiation, we can have any number of excitations there, not just 0 or 1. So you need a number of qubits to match the number of excitations that you have. We then model the interaction with gates acting between the mode qubits and the atomic qubits. And so we can actually look at what our circuit will really look like in something like this. So like I said, we have our initialization and our trauberization. Our initialization is simple. We just excite all of our atoms. This means we begin in an initial state with all of our atoms in the excited state and all of our radiated modes empty. Then inside each Trotter step, so every small time evolution, we set the frequencies of each of the atoms and each of the radiated modes. And then we then have to couple every single atom to the entire field. And since we're only using 2 qubit gates and single qubit gates, we have to do this one at a time. So for atom alpha, we couple that to mode 1, mode 2, all the way up to the number of modes that we have. And then within there, we have our actual fundamental gates, where we are coupling our alpha atom to our kth mode. So this is our circuit, and we essentially just have this a bunch of times between however many atoms we have, however many modes we have. And so the number of gates that we are using actually grows relatively quickly. And so what that means is that a lot of the quantum hardware that is available right now cannot handle very big simulations with this. So what we are doing is we have used a classical quantum simulator, and the results that I show you up until the last result will be with that simulator. So when we're looking at our results, the first thing that we wanted to do is to make sure that this algorithm can actually reproduce well-known things. So what we're going to look at first is a spectrally homogeneous ensemble. And just as a reminder, when I say spectrally homogeneous, what I mean is that if we look at the emission spectrum from a single emitter, that will overlap exactly with the emission spectrum from separately the next emitter and the next and the next. This is not to say that the total collective measured emission spectrum will look like this. It's just to say that the emission spectrum of an individual emitter will look like this, and all of them look the same. So one of the big results of super gradients is that as you increase the number of emitters in the ensemble, the maximum intensity that you reach also increases, and we are able to reproduce this quite well. So we can see as we range our number of atoms from 1 to 7, we get the super radiant peak emerging when n is equal to 3, when we expect, and rising up to 7. We then have the notion that this should scale as the number of atoms in the ensemble squared. So that is exactly what we have matched. So what you see in the data here is both the intensity, the maximum intensity, and the maximum coherence calculated both by our algorithm and just by integrating the master equation, so doing a classical computation approach. Then what we do is we fit both of those, and we see, one, they match exactly, and two, the intensity does scale very nearly as n squared, which is what we want. So that's it. Next, we want to look at some more novel things, or leading towards novel things, by looking at especially inhomogeneous ensemble. So here, we're going to have 4 atoms only, and we're going to place them at distinct locations in frequency space. And what we're going to vary on the next slide, and what we're really interested in, is how this cooperation depends on gamma naught, or the width of these emission spectra. So we expect that as we increase gamma naught, we get greater and greater overlap, and therefore we would expect greater and greater cooperation. So let's see. It turns out that is indeed true. So if you look on the left-hand plot, if you look at panel A, what we're looking at is an increasing overlap, or an increasing gamma naught, leads to an increase in that peak intensity from that ensemble. Panels B and C show you the emission spectrum as calculated by the algorithm for the very small gamma case and the relatively large gamma case. And we see that these are trending towards what would be the value for non-interacting atoms, towards the what we would have if we have completely resonant atoms or homogeneous ensemble. Now, on the right-hand side, we're looking at the coherence. So if you integrate using a master equation, then what you will see is these dotted lines. But as we increase gamma, we are increasing also this cooperation, so our coherence is also increasing, getting closer and closer to that ideal case. So this also works. So that's good. Now, I mentioned before that what we were using here was a classical simulator of a quantum computer, but that's not to say that we cannot run these systems on a quantum computer. In fact, we did. It's just that when we do that, we find that it's noisier, just because of the state of current quantum hardware that is free. So this is what we find. It absolutely does work. We can calculate the emission spectrum for this. It's a single emitter in a bath of 7 ensembles, so no collective effects here. Sorry, in a bath of 7 modes, so no collective effects here, but we do see the emission spectrum doing exactly what we would expect it to do. So, just to summarize, these simulations match typical results in classical computation within the regimes of validity, and it is also very straightforward to extract non-trivial and novel results with this algorithm, at least more so than it is using something like a master equation approach. And also, these algorithms will be there and be ready as quantum computers get better to implement bigger and bigger system sizes and maybe see new results. So, thank you very much.
Okay, thanks for the talk. Any questions?
That's not something that we have worked on, but that is definitely something that we have thought about.
Any other question? Okay, let's thank the speaker again.
I'm a graduate student in the Portuguese School at the University of London. My talk today is about optimizing particular gates in quantum solutions. And I'll begin with stating the importance of high quantum interactions. So high quantum interactions consistency and coherent immutable nature are key ingredients in the quantum architecture today. And optimizing these interactions is a path towards scalable quantum platforms. Right? In particular, in this work, we focus on cavity-mediated intermediates, which are essentially just fundamental quantum operations, logical operations, which are implemented by coupling the two qubits via a cavity, right? And as shown in this sketch below. We particularly focus on these transfer of quantum state from qubit 1 to qubit 2 via the cavity, and already you can see that there are several parameters at play here. The frequencies of the qubits, the frequency of the cavity, the coupling strengths can be different, and the damping itself. So there are various parameters at play, and the efficiency of state transfer in such a system needs to be characterized so that it can guide experimentalists towards the optimization process that I just discussed. Right? More formally, we study such a quantum state transfer process using the two-qubit quantum Rabi model. Here, the two qubits are described with two spheres operating at frequencies omega 1 and omega 2. They're coupled to the cavity with strengths G1 and G2, and the cavity itself is operating at a frequency omega C. The cavity is also damped by coupling the same corresponding tau. We define the decodings, which are the difference in frequencies between individual qubits and the cavities, as delta. And the Hamiltonian below is essentially just the qubit cavity energies and the coupling interactions between each qubit and the cavity. You will note that I've also included the energy non-conserving terms in purple in this interaction, and this is something I'll touch upon towards the end of the talk. Right? And so how do we solve such a model? We adopt quantum algorithms. Why? Because first, on one hand, it's intuitive. We directly encode the Hamiltonian on the circuits and walk them, and then affords you the ability to completely and directly track the individual and collective behaviors of the system, as I show. And essentially, we're simulating quantum systems in a quantum way. Right? The more obvious benefit, obviously, is that it can scale to larger quantum systems, but clearly here we're using a very small system that can be solved classically. But the point is that such a model can be trivially extended to represent much larger systems such as cavity arrays, spin networks, and processes such as superradiance or spontaneous emission. In fact, spontaneous emission is something we study with quantum algorithms, and that's something that we did last year. Right? So clearly, quantum algorithms have some benefits, and mainly in the regime that it avoids some of the approximations that are involved with classical approaches and the abstraction that comes with those approximations. Right? So how do we implement such quantum algorithms? We take our Hamiltonian and we map the operators in Hamiltonian onto qubit operators, which are essentially just poly gates. In doing so, we also map the cavity operators as two-level systems, which is a reasonable approximation if you just have one excitation in the system and you're not operating in the Understown countries or the deep dispersal regimes. Right? And once you have this qubit Hamiltonian, we can just build the evolution operator from it and then evolve the system in a stepwise manner using the shreeky cross decomposition. Okay? The simulation itself is represented using a quantum circuit. Here we have the two qubits that I showed in the model and the cavity in between. Essentially, in our discussion, we're going to be looking at the transfer of the excitation from qubit 1 through the cavity, from qubit 1 to the cavity into qubit 2. So we first initialize qubit 1 to its excited state, and then we run it through a series of Carter steps, which is essentially simulating the evolution of the system. And if you look at it, each Carter step is essentially just a snapshot of the Hamiltonian that we discussed. Right? The blue boxes are phase rotations that correspond to the energy evolution of the qubits, and the red boxes are the two qubit gates that represent the couplings between each qubit and the cavity. Right? And so once we are done with these steps, we can just measure them in whichever way is convenient to us, depending on what we want to see. So we ran the simulations on a simulator, but then these circuits are compatible with the optimized hardware quantum hardware. So we move on to results, and first we look at the case where we look at the efficiency of the state transfer process as a function of the qubits. That's essentially the difference in frequencies between the qubits and the cavity. Right? On the left panel we have the short-term dynamics, and on the right panel we have the long-term dynamics. At the top we have the occupation of the qubit 1, cavity, and then qubit 2. Right? So visually we see that there are only two situations where you can expect complete transfer. One, when both the qubits are resonant with the cavity, and that's represented by the red line here. So the excitation starts to drop away from qubit 1, builds up into the cavity, and then ends up in qubit 2. Right? The other scenario is the dispersal regime, where both the qubits are resonant with each other, but they decouple from the cavity. So they have some kind of an effective coupling via the cavity or virtual coupling, and that also facilitates complete transfer, represented by the blue line, however, over a longer time. Right? And And in general, when you have unequal couplings between the qubits, unequal detunings between the qubits, you notice that the state transfer is very, very minimal, right? Here we do the same process, but in a broader way. We look at several combinations of the detunings between the two qubits, 10 to 1 and 10 to 2, and we observe clearly that this is the middle spot is just the resonant regime which we discussed, and the far ends of the diagonal are the dispersive regime, which we also discussed, and correspondingly the resonant transfer happens much faster. The right panel, which shows you the blue heat map, essentially is the time it takes to reach the maximum fidelity, right? And we also observe through this algorithm that we have that we are able to observe a non-trivial high fidelity transfer even in the intermediate regime. So when your detunings are comparable to the couplings between 2 and 4G, we're able to see that we are able to get 99% fidelity or higher with the second swap in the qubit between. So essentially the excitation is swapping between the two qubits, and in the second swap, we're able to see that we're able to get 99% or higher fidelities. Next, we move on to switching the couplings. So far we discussed a case where the couplings were equal between the two qubits in the cavity, but now we make them asymmetric, and immediately the cases which we just discussed as high fidelity cases break down, definitely lowers. However, we use an intuition here in that essentially what's happening in these these high fidelity processes is that you have a similar or an exactly equal Rabi frequency between the individual qubit cavity interactions, right? So, and this Rabi frequency is a function of the couplings and the detunings. So if you have a difference in the couplings, maybe we should be able to change the detunings such that your effective Rabi frequency in a sense matches, and you kind of create an in-phase process that allows for high fidelity transfer. This is exactly what we see. So we consider the case of 5Q qubits, and which normally give you just less than 1% fidelity. But when we introduce an asymmetry in their couplings, we're able to match their phases in their absence and produce fidelities up to 95%. So that's the takeaway here. We next move on to look at damping. We have our same circuit, but then to that we've attached amplitude damping circuit thanks to Gupta and Lu. And what this amplitude damping circuit does essentially is just rotate away excitation from the cavity step by step by measuring it at the rate kappa, right? And the results here are quite interesting too. So we classify them into two sections. One is the resonant transfer, and the other is the dispersive transfer. At the top panels represent the populations of the qubits in the cavity, and the bottom panels represent the coherences between them, right? So the light blue line represents a weaker damping, and the dark blue line represents a higher damping. So clearly we see that the dispersive regime is much more resistant to cavity damping than the resonant regime, and that's simply because in the dispersive regime you have virtual mediation through the cavity, and the cavity is only minimally populated, right? And that's reflected in these coherences below. Whereas in the resonant cases, the dominant coherences are the qubit cavity coherences, represented by the green and the gray lines. In the dispersive case, the dominant coherence is the qubit coherence, which is represented by the magenta line, right? And this is also the beauty of quantum algorithms, that as the systems become larger, you can very cleanly track coherences or whatever you want between particular systems without having to approximate or average away interactions. Right? And finally, we look at something called the rotating wave approximation. It's a very common approximation in these studies, where the energy non-conserving terms in Hamilton domain is dropped, and that's fine as long as your couplings and the detunings are much smaller than the cavity frequency. But when they're not, when you're approaching a ultra-strong coupling regime, as in this figure, you see that the RWA or this approximation does not capture that effect at all. In reality, what happens as is seen in the simulations is that the fidelity starts to break down. So that's something we're able to capture with algorithms. And also, in the dispersive regime, when your detunings are really large, you end up with some kind of an asymmetry in the time it takes to reach that maximum fidelity. Right? That's again missed by the RWA and our algorithms are able to capture. So with that, I'd just like to conclude that quantum algorithms allow us to look at a broad characterization of the systems, and that they can be extended to look at larger systems in quantum information. Thank you.
Great, thanks. Questions? Okay, so we can send the speaker one.